You're finishing up by tonight the Chapter 11 homework in Launchpad, and I'm getting reports of issues. Taylor's just asking me about the one question that says, it's question 11.3 in the book, and it says, all of these coefficients are positive. Is that what you would expect? And it says, if you're looking in the book, it says high school rank. And would you expect your GPA to be higher if your rank is higher? And I think it's just, to use Taylor's phrase, semantics of what we mean by rank. The answer, that's an odd numbered question, so there is an answer in the back of the text. And what they say is, math GPA should increase when any explanatory variable increases. But Taylor's point is, well, rank, like if you're first in your class, that's a rank of 1. Well, apparently they're defining rank the other way. As your rank goes up, as you're better and better, then your GPA should go up. But it's really backwards, because rank 1, and the worst, if you got 500 kids in your class, the worst kid is ranked 500. So that's a bigger number, you'd expect a lower GPA. Right?
It should be inversely correlated.
So just think of it as high rank means good. Right? So high rank isn't going to a small number. Think of it as, rank of which best are you, right? I'm the
first best.
Yeah. Go ahead.
Like when you're talking about ranks, you say like working your way up the leaderboard. That's working your way up to 1. So
Right, right. And so that's Taylor's argument, that it's kind of backwards of what it should be. But when you go to answer that question, just know
Again,
that
if you increase in rank, you're
Yeah.
up, but if you move from rank 3 to rank 2,
Yeah.
you're going to say you're rank 2, so you should plug into the model.
So I suspect when the author wrote that question, they're thinking higher rank, higher GPA, yeah. But without thinking numerically, what does higher rank mean? It actually would mean a lower number. But so
they're worrying about the number, not how is it correlated?
they're not worried about the number.
Okay.
Right. And they should be. Yep.
can we go back and see all the problems we missed?
Yes.
Yeah, you can review your answers. I don't remember exactly how to do it, but I know that you can. You can
If
go
you
back.
click on it, you can click Review Submissions. And then
Review
it'll,
submissions.
and then it'll
Okay.
pull up a list of all the problems you've done, and you just click on the one that you want to review.
And it will show me what I missed and what it should
Yeah.
be.
Now, I know that Laura had an issue. There's one question that has you enter like 6 different things and round to the 4 decimal places.
That's the
And
same question.
is it just later down? And so some of it isn't rounding right, or it's, I don't know, it was off at like the 4th decimal place.
They're doing it with software, and I did it with computer.
Yeah, so it's probably a matter of, if you round it during intermediate steps, you're going to be off a little bit, right? Email me if that's an issue, and take a screenshot like Laura did, so I can see, yeah, she's got the right number, and then I'll just give you those points back. You don't have to go back and, I mean, well, you can't go back, right? You can only get one attempt, but,
Yeah, I didn't know that.
so. You didn't know that?
No.
Yeah, well. Yeah, we did say that in class last time. So, I'm not aware of other issues. Well, I actually haven't read all your notes.
There's another one that and I don't know, maybe I just didn't understand it, but it was asking for the R squared, I think, and they gave you the numbers in the table,
Uh-huh.
but the answer doesn't use those numbers.
It looks like it's an older problem.
So,
I emailed you that one.
okay, I didn't catch that. I was trying to catch errors,
And then
and I did call, or I emailed the Launchpad people to complain about these issues, and I did get a response back saying, hey, if you want, I can show you how you can change the answer. I can't do it in those algorithmic questions, but I can do it on the ones I'm now using. So I can go in and fix it, but I have to know that there's a problem before I would know to do that. So
So you're basically beta testing their software.
pretty much. And it does say, when on my instructor's thing, it says homework beta. So, yeah.
There's also another one on the very last problem that if you put a negative in, it'll count you wrong, and it's a negative answer. So I had the right answer and it was negative, and the answer provided was also the same, but it didn't like. my
So it
answer.
counted you wrong, but
Yeah.
showed the correct answer as the
It's
same thing you entered.
As I had.
Okay. Yeah. That ain't good.
No.
We're beta testing now.
So, so yeah, just email me those kind of things, and I'll restore the points. And you know, this is part of my motivation as an instructor for using this is it saves me grading time, because I'm a slow grader, as you realize. But if all these issues, it takes me longer to get through than it does just to grade the dang homework. So, but we'll persist as best we can. So, last time we were talking about ANOVA, and we had just finished going through the ANOVA table, right? So we've started chapter 12. I will not get all the way through the rest of chapter 12 today. I could if all I did was what's in the book. I'm going to do some Excel and SAS stuff as well today, and that'll lead up to some time. But any questions on the one-way ANOVA table that we went through last time? It's a little different than regression, but it's basically the same idea. Instead of having a line that you're fitting and the mean is, or the predicted values come from that line, you're now, think of your predicted values as being, well, the predicted value for somebody in this group would be whatever that group mean is. So the predicted values are all kind of the same within a group, and then the groups change. And they don't have to change in a linear way like they did before. Okay? So, did I get to any data last time? There's an example in the book that I'm going to go through just because you have it there that you can look at the answers, or you can look at the output and try to match numbers when we go to electronic. But this is example 12.3 on page 648 of the book, and it I'll read you the first part of it so that I don't mess up in how I word it. But this is about Facebook. Everybody loves Facebook, right? And in Facebook, it's number of friends. So our friends in the psychology department always are doing interesting studies about kind of social interaction and that kind of stuff. So they did this study, and the idea of how many friends you have on Facebook, is that an indicator of social attractiveness? Okay, so among college students on Facebook, the average number of Facebook friends has been estimated to be around 281. Right? Please don't go look for me on Facebook. I had to get a Facebook page once, then all my cousins found me, and all my old high school friends found me. I don't like Facebook, and I probably have like 38 friends, something like that. And now every time I get a friend request, nope, 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 nope. So my social attractiveness is low. Right? College kids have 281 on average. So an experiment was run to examine the relationship between the number of Facebook friends and the user's perceived social attractiveness. So a total of 134 undergraduate participants. So these are students that they brought in to run this experiment on. So they're the test subjects, right? They were randomly assigned to observe one of 5 Facebook profiles. So the idea is they come in, they sit down at the computer, and they say, here's a Facebook profile of a person. And it's a fictitious person. And there's 5 of them. And each of those 5, you can see when you get on Facebook how many friends that person has, right? And so they either had 102 friends, 302 friends, 502, 702, or 902. Now, why'd they pick 02? Because it'd be suspicious if it was exactly 100, 300, right? So close to that. And then after viewing the profile, each participant was asked to fill out a questionnaire on the physical and social attractiveness of the profile user. Each score is an average of the several 7-point questionnaire items. So strongly disagree to strongly agree. So they give a summary of that, and everything about the profile, including the picture, was identical between the 5. The only thing different was how many friends that person had. Got it? So if the number of friends, so wait, before I finish that sentence, what are they trying to find out in this study? What's the purpose of this research study?
How does friends affect social attractiveness?
Yeah, how does number of friends affect social attractiveness? Okay?
What is
And
social attractiveness?
Don't go there. Just, how does number of friends, right? So the only thing different is the number of friends, right? So what's the null hypothesis?
That there's no difference.
There's no difference. So the 134 participants are divided between these 5. Now 134 is not evenly divisible by 5. So they had different sample sizes. They don't explain why they would have very dramatically different sample sizes, but they are pretty different. The most was 33 and the least was 21. But probably it's just a matter of people agreeing to be in the study, getting randomized to a group, and then never showing up to do it. That's usually what happens. Right? So we've got 5 groups. And so in our notation that we use for ANOVA, what is this 5? That's capital I. I didn't ask that question in a very good way, but you understood. So 5 groups implies that capital I is 5, right? So in our ANOVA table, remember we have source, and we call that group, or and we use several other words. And I'm going to put in parentheses under it, and I forgot my symbol for number, so fix that. Group, so this is number of friends, right? Now it's a categorical variable, so we're not going to use the actual 102, 302, 502. It's just group 1, group 2, group 3, up to group 5. Got it? Okay, so then you have a line for error, and then a line for total, just like you're used to. And then degrees of freedom. So fill in degrees of freedom. How many degrees of freedom for the group variable? Or,
minus 1?
the other word that we use is factor. Right? What'd you say?
Is it I minus 1?
It's I minus 1, so that's going to be 4. Okay? Total degrees of freedom?
133.
133. And it's the same as it was for regression. It's 1 less than the sample size. Right? So total degrees of freedom is 133. So N with no subscript, remember, is the grand count, total sample size. And then the number of people in each of the groups we labeled as N sub 1, N sub 2, and so on. So N with no subscript is the overall mean. So this is 133. Now how much for error? And how do you get that?
It would be the N minus I.
Okay? And you get it just by subtraction, right? So it's N minus 1 minus I minus 1, which is N minus I, which is 129. Okay? And then, just like in regression, you have sum of squares, and you have mean square, then you have an F, and a p-value for that f. Now I wrote it the way that SAS writes it, with this PR greater than f. And what does PR stand for?
Probability.
Probability. So PR for probability. So probability of being greater than f. That's p-value. So some tables will call it p-value, some call it different things, but just recognize that's what it is. Okay? So let me pull up an Excel spreadsheet that contains this data, and then we'll produce this and discuss it. So let me zoom a little here. So all of this stuff, ignore. I did this, and I'm going to show you how to do this. This is the data set when you load it, right? So they'll almost all be set up this way, whether they come out of this textbook or anything else. And notice the columns. So friends, that's my grouping variable. So they've named that friends. And it's a 102 for every one that you can see on this page. And then if I scroll down, oh yeah, you do that. Then it jumps to 302, right? So at the 25th observation, well, that's not the right word. The 25th row of the Excel spreadsheet was the last row with a 102. But remember, the top row had the headers in it. So there's 24 people in that first group, the 102, right? So they're just strung down till I get to 134. I won't scroll all the way down with the grouping variable as the left column. And then B is participant. What does that mean? Column B. It's just, yeah, it's like a subject ID number. Subject number 1, subject number 2, whatever. We will not use that variable in an ANOVA. In an analysis of variance of this data, that variable is no good. It doesn't help us. So you can ignore that variable, and then the dependent variable is their score. They were supposed to rank on several questions, and then they averaged those questions, and they came up with the score that that person, that participant gave to that particular profile. Everybody understand the setup? All right? Now, to do an analysis of variance in Excel, you can't have the data set up in one long string. It needs to be set up, and you can do it either as rows or columns. I chose columns, but you could have friends 102 and then participant 1, participant 2, 3, 4, and strung out 24 this way. Right? So they're set up in, and either way is fine. But they have to be in separate columns or separate rows. So what I did is I took my mouse and I drug across those 24 observations for 102, and I copied and I pasted them over here. And in the top row, I put the name of that group. Now this particular data set's kind of funny because the names of the groups are also numbers. But that's just a name. Right? We're not going to use that number. So there's your 24 observations for group 1, and you can see that group 2 has the most. That's going to be your 33, and so on. Got it? Okay, so now let me delete the ANOVA table that I already ran in advance, and I'm going to reproduce it. And I'm going to get rid of all these lines because I may get in the wrong position and not get the lines to match up. So there's my data set up in the correct way. So you kind of learn, best thing you can do as a student is learn to teach yourself, right, when you get stuck. So what would you try? Trial and error. I remember once a professor I had when I was in studying computer science classes, and he said, well, just try something. You're not going to break the thing.
So
Right.
you can try formulas.
Okay?
Most have.
You could try formulas. All right? So if I click Forget, I can click with my finger. If you click on formulas and you scroll around, you look for a formula that talks about ANOVA. Guess what?
There isn't.
There isn't. But I go to category, then statistical, and
No.
there's nothing for ANOVA. Okay? Good try. Didn't work. Try something else.
No, it's probably data.
Data. Then data analysis. Ooh, ANOVA. And I don't know why, but it always comes up, for me at least, with the random number generation as the highlighted one, which means there's some above this. So if you scroll up, then you see ANOVA single factor, ANOVA two factor with replication, two factor without replication, blah, blah, blah. But at least there's the ANOVA. Which one do we want? Single factor. So we'll say okay on that one. Now, input range. What do you think? You want to highlight the entire columns and rows, right? And I don't think I can do that with my finger, so I'm going to use the mouse. But and notice there is a checkbox here that says labels in first row. So I'm going to go ahead and grab that first row so that it names them with the right names. So drag across all of those and check labels in first row, and then output range. And again, remember, when you click output range, it jumps the cursor back up here, which really hacks me off. So then you got to click in this box to put the cursor back down there, then click where you want it to go. And you don't have to click a range of cells, you just click where you want it to start, just like with regression. So I'm clicking that box, then I'm going to come up here and click that cell. And you can choose a new worksheet if you want, but that's fine. So I'll say okay to that. Question?
Remember that error I got that we couldn't figure out how to fix? It was because I was hitting the F, G, H, whatever, and for whatever reason, it did not want to spit anything out when I selected those. So I wanted the whole thing up and down, but I couldn't click F to do it.
So rather than drag across, you have to tell it where to stop. If you click up here to infinity,
Yeah,
it doesn't like
that's
that.
why it
'Cause
flipped
it's
out.
trying to set sample size, and yeah, good call. Okay, so if I drag that over here, there's the ANOVA table, right? So in Excel, the first thing it produces is not part of the ANOVA table. It's just a summary of the groups. So it's telling me, okay, here's your groups, here's their names, 102, 302, 502, and so on. Here are the counts. So those are labeled what in our notation? 24, 33, 26, what are those?
Little r?
Okay, the number in each group, which is, what's our notation for that? N sub, so this is N sub 1, N sub 2, N sub 3, N sub 4, N sub 5. Got it? And then sum, average, and variance. Those should be fairly explanatory. Variance is maybe not quite as explanatory, but if you take the square root of the variance, you get standard deviation in that group. Right? So now I'm going to scroll up to the ANOVA table, and Excel just has the default width of the column, so if you can't read the whole column, you can always make that column a little bit wider. I don't know, can I do that here? That didn't seem to work.
Try to,
If you double tap.
yeah, double tap between the two lines.
Ha! Good call. All right. Okay, so now we see between groups, within groups. Ooh, that's different than the words I used a minute ago. Remember we had that discussion that the variance, the variation of the means. Remember we had some box plots, and some of them were high and some of them were low. The variation between the means, that's between group variation. Right? And then within groups, that's your error. Right? So this is explained variability and unexplained variability. So think about rather than a regression line, you've got those box plots or whatever, the variability within a group. That's those standard deviations, those variances that we were just looking at, right? That's within group. So that's error. That's unexplained by what group you're in. The reason that these people are different from each other is not explained by what group they're in, because they're all in the same group. So that's error. And then you have total. All right, so scroll this over. Okay, so now everything works the way that you're used to. I never noticed, but Excel in ANOVA reverses the degrees of freedom column and the sum of squares column. No big deal, but
You're just dividing them, right? You just divide sum squared by degrees.
that's
of
right.
freedom.
So how do you get mean squared? You just divide sum of squares by degrees of freedom. So 19.89 is the sum of squares for groups. Divide by 4, you get 4.97. Okay? Error degrees of freedom is 129. You divide the sum of squares error by 129, you get 1.2. So the F statistic now, how do you get that?
Mean squares divided by.
The mean square for group divided by the mean squared error. So 4.97 divided by 1.2 gives you 4.14. And then Excel calls it p-value, which is handy because that's what it is. And it's 0.0034. So what's your conclusion?
Reject.
There's a difference.
Okay, reject the null. There is a difference. Keep going.
Between
The
friend groups.
Okay.
the popularity.
There is a difference in the means for at least one of those 5 groups, right? The group means are not all equal. There's at least one of them that's different. So how do I know which one is different? Or maybe there's some ordering to them, or how do I know?
Graphic.
Okay, good. You want to see a
The eyeball
graph?
test.
Here's the table of means, so you can look at that. Do any of these look dramatically different than the others?
161.
It's really funny.
What'd you say?
The 902 is the lowest.
Oh, the 9.
902 is the highest.
I thought you said, I was looking for a number in here that, I thought you said 192 or something. But 3.99 for 902, and 102 is 3.81, but it peaks at 302. So these aren't, there's not a linear progression, right? It's like, if you got too many friends, then that strikes against you, right? So if somebody's got almost 1,000 friends, there's something wrong with this person. They're not socially attractive. I don't know. But so a plot of these means would be very useful, right? Excel doesn't do it automatically, but if you have this table, which is automatically created, it's pretty easy then to plot those values with this on your x-axis. You know how to do that. Yeah.
Speaking of this in a different context, my professor was telling me a story when they were looking for a new chair of physics at the place he was, that they were looking for the best applicant. And you know how they make you do research papers and where your name's attached to stuff. He says, we ran upon this one guy that they thought was just absolutely, we had to have this guy. And he looked at all of his publishing history, and it was enormous. And he said, we got to skip this guy because there's no way that's reasonable. And that may be what
So
you're staring at there. There's something wrong here.
Yeah, so
Because
too
you
many
can't
publications
possibly
was-
have done anything
Right,
wrong.
so there's an optimum value. Too many is a signal that something's wrong. It's this, so in that case, it seems like he was probably lying. He didn't have that many because it's not possible to have that. So yeah, that's possibly what's going on. Okay. So remember the way we write out the null hypothesis in a one-way ANOVA setting. mu1 equal mu2 equal mu3 ... to mu5 in this case, right? And then the alternative is at least one of those means is different from the other. Okay, now I want to talk, before we go to SAS, we're going to do this with SAS, but this number, 1.2, what does that represent? Yeah, it's the mean squared error. What is it? 1.2 what? What is the mean squared error in an ANOVA setting? In a one-way ANOVA setting?
Variation.
Okay, we don't have residuals so much in the ANOVA setting, but it's the same kind of idea.
Variation within
Variation within the
the groups.
groups, that's right. So that's variation within the groups, and this is your pooled estimate of within group standard deviations. So here are the within group variances, right? Give me a pooled estimate of those. How do I do that?
Would you average them? Is that easy?
What I want to do is I want to keep those numbers and be able to write on here. Can I do that?
The variance on 702 is
Yeah, if
actually,
you add the little thing again, you can write over Excel.
Yeah, if I do that, right?
Yeah.
Now, how do I get back to my Excel icon? Ah, I gotta use the mouse. I can't handle that.
You need to actually click on the mouse thing up there.
Click on the mouse thing. I don't see a mouse thing. I don't know what you're talking
A little arrow thing.
Yeah. Just add the five together. What is that?
about. I was so worried about this, I didn't notice my Excel spreadsheet was already there where I wanted it to be. God, I hate me. Okay, so here we go. We got these 5 variances. We want to pool them. Now, how would you pool them? Well, what that means is ignore groups, right? And now I got 134 observations. What's the variance of those 134 observations? Okay. Well, the variance, remember, is the sum of xi minus x bar quantity squared divided by n minus 1. Right, that's his formula for variance. But now these are within a group. So I can make this an x bar sub j and an n sub j. And I got it. So if I take each of these variance estimates and I multiply by the thing on the bottom for that group, then I get the total sum of squares within that group. Then if I sum across those, I get the overall total sum of squares. Right? So let's do that. Let's take 0.99, and I want you to do this on your calculator. I'm going to round to 4 places. 0.9979 would be 80. Multiply that by 1 less than the count in that group. So that would be 23.
22.954.
Okay, I don't want all the numbers yet. I want to string the whole thing out and then tell me the sum,
Okay.
right? Because I'll never remember those numbers. So then the next group has 33 in it, so that's 32 times 0.7248 plus, and I'm going to come down here. I need some more room. Next group has 26 in it, so 25 times its variance. 1457. Fourth group has 30, so 29 times its variance. 03, ooh, that's a 995, so rounding to 4 places would make that 0400. I gotta use my eraser. 0400. And then the last group has 21 in it, so 20 times 1.0459. Whew. So what do you get?
154.8681.
154 point what?
8681.
8681. Okay? Do you see that number on the ANOVA table anywhere?
Yeah.
Right there.
Within round off error, that's sum of squares due to error.
So that's pooled error.
You should be going, that's amazing.
Oh, it makes sense.
Well,
Yeah, it
it's
makes
in
sense.
group, pooled error.
That's
Yeah.
the pooled, that's what that within group says. It's the pooled estimate of within group error, within group standard deviation. So now, if I divide that number,
Just leave it here instead.
if I divide that number by, okay, the sum of ni minus 1, which is all of those coefficients, right? So it's a weighted mean of those variances. So this one got a weight of 23. Now I need to add the weights, right? So it's 23 plus 32 plus 25 plus 29 plus 20. That's what those things would sum up to. What is that equal to?
Guessing 144.
You're guessing, yeah, and that's exactly right. Because you subtracted 1 from each of the ends. And how many ends are there? 5. And what's our formula for the degrees of freedom for within group? N
Minus I.
minus I. So it'd be 134 minus 5. So the NI's, these numbers, 24, 33, 26, 30, and 21, those add to 134, and then each one of them has a minus 1 on it, so you've subtracted 5, so this is going to be 129.
Just blew my mind.
Now, you divide that number, 154.86 whatever, by the 129, you get the mean square. So what is this an estimate of?
The variability within groups.
Okay, it's variability within groups, pooled estimate of the within group variance. So we will label that as S sub P. And it's squared because it's a variance, right? So SP squared is pooled within group variance. So then SP would be the pooled within group standard deviation.
And that would be the within group MSE. Yes?
This is the within group MSE, right?
Yeah, that's what I was saying. Down here, this 1.2005, that would be SP squared.
That's right. Good, good. So S sub P squared is that number. So what's SP? Duh. Just the square root of it, right? So the square root of the MSE is your pooled estimate of standard deviation.
Do we still call it MSC, root MSC?
Root MSE for one-way ANOVA, just like for multiple regression.
MSWG.
Yeah, don't go there. I think the book maybe actually uses that. MS, well, I'm not sure they do. What was the notation? Instead of SP, when we were doing multiple regression, what did we call this thing? S sub, man, how quickly you forget. You just flush right after a
It's just
test.
SE.
SE. So S sub E was root mean squared error in a regression setting. We now call it S sub P, but it's the same idea.
I just never arrived as a sub, so I just was confused.
So things are a little different when this is a categorical variable, but it's the same idea. It's like I want to explain variability in my Y variable. So what's my predicted value? Well, now it's I predict the value. My predicted value for somebody who looked at a Facebook page with 102 friends, my predicted value for that next person would be 3.81. I predict they're going to have a score of 3.81 because that's the mean of everybody that looks at that many friends. Right? Okay, everybody got what they need off of here, because I have to get it erased.
I want a photograph of that real quick.
Put that on Facebook and tag him.
Yeah. Then
If you can
I'd
find-
lose friends.
So is that a coincidence that if you average the variances, you also get 1.2?
If you average the
If you average
variance,
the variances of all the groups, you get 1.2.
it is,
also. Is that a
um,
coincidence?
it is a coincidence, but that will often happen. What if I had exactly identical sample sizes? Then,
That variance.
then this would be exactly equal to the average of the variance. So this is a weighted mean weighted by sample size. If the sample sizes are really unequal, then you'll be further from just averaging them, right?
Okay.
So if I just average them, I'm not weighting them by their sample size. But here the sample sizes are, they're not real close, 21 versus 33 min to max, but it's, you still get to one decimal place 1.2. You wouldn't get all the rest of that.
Yeah.
Okay? So let's clean all that off. And let's go run this in SAS, which then automatically gives you some graphs and things like that as well. All right? Ooh, I got about 5 minutes left, so that's plenty of time. Do that. Oh, I'm still annotating my desktop. So here, I've already imported this data and ran this already, so I already have output. But when you do it, you won't. So the first thing you do is you read in the data. So this is the friends data. Everybody knows how to do that by now, right? Get it, open an Excel spreadsheet, pull it into SAS. Well, once you're into SAS, I'm going to say modify tasks because I've already done it once, but you'll start here with tasks. So push tasks, and then there's an ANOVA. Right? So you click on ANOVA, and then one-way ANOVA, non-parametric one-way ANOVA, linear models, mixed models. Right? So we'll click on one-way ANOVA.
Do we not use one-way ANOVA?
Huh?
Do we not use one-way ANOVA?
Well, I'm actually surprised. I expected when I popped that open, they would have one-way ANOVA, two-way ANOVA, but then they just call that linear models. Since it's in the ANOVA setting, not the regression setting, it has a little bit different connotation. But if I do linear models, it'll work also. Now, behind the scenes, what's going on in SAS is ANOVA, one-way ANOVA, will not, it won't act, how do I say this? It won't perform correctly if there's missing values. And so you would want to use linear models. And this uses something called proc ANOVA. Linear models uses something called proc GLN, which is short for general linear models.
Or compile.
What's that?
The code will compile.
Yeah. So we'll do one-way ANOVA here. And then you have your 3 columns of data. Remember, the participant variable is meaningless. We don't want to use it. So friends, which,
Would you group analysis by friends?
that's the group. So no, you don't group by that. That's your independent variable, right? Which is a great question. What is that group analysis by? What does that ask?
Like if you had male, female, you want to see the results of how they work.
Yeah. So in SAS, what's called a by variable means do this separately for the different levels of that. So if I put gender in there as a group analysis by variable, then it'll give me a one-way ANOVA on friends for females and a one-way ANOVA for males, completely separate.
So it's just something to do two tests within one, right?
Well, it's not even within one. It's just saying, okay, got the data sorted by this subgroup variable, and I want a different analysis in each of those subgroups. Right? So then score is my dependent variable, so drag it across to to dependent variable. And then over here, just like with regression, you have different menu options, and you can set it so you get different outputs. So data I'm done with. If we look at tests, none of these mean anything to you, so that's probably a clue that I don't want to do those. But this is Welch's variance weighted ANOVA, then Bartlett's test. These are tests for equal variance. Have I remembered to say that? One of the assumptions necessary for ANOVA to be valid is that the groups have equal variances. Remember in regression we had to have constant variance? This is related to that. Okay.
Groups have equal variance?
Groups have equal variances. And the second assumption that has to be met is that within each group, the data are normally distributed. So you have normally distributed data. So very similar to regression again. Only in regression setting, you didn't necessarily have different groups. It's just different levels of X. Then you had to have a normal distribution and the same variance. But that's really the same thing. So these tests for equal variance are three different guys that came up with ways to test whether those variances are equal. So we won't deal with those in this class. All right? So I don't care about tests. So if I go to means, then it highlights the word comparison, and it says the main effect is friends. Okay, when we get to chapter 13, we'll learn that term, main effect versus interaction effect. All right, so for now, main effect just means the effect due to the variable friends. And then methods to use, these are called multiple comparisons methods. And I don't have time today to do this. This is the second half of section 12.2. But for now, we're going to learn this one, the top one called Bonferroni. I'm going to click that one. We'll learn that on Wednesday. Okay? And then I'm going to click, the next thing down is plots. So I can ask for a means plot or a box and whisker plot, or both. I might as well have both. It's free. Then means plot options, you can choose standard deviation or standard error. I'm going to choose standard error, not that it makes a whole lot of difference. But, and then use pooled variance. Yeah, I probably want to use pooled variance. But these are just plots. They're not affecting the statistics that are done. Then if I click on results, I could save an output data set like we did a couple of times because we wanted to see predicted values. I don't need to do that today. So everything's set the way I want, so I'm just going to run it. And this is the old output. I think it's still running. There's the new output. It's going to be identical. Top part gives me information about the data set. Right? And then the ANOVA table looks identical to what we just saw in Excel, same numbers. Things are reordered a little bit, same p-value, same f statistic, gives you an r-square value. Where does r-square come from? Same as in regression. It's the mean square for or sum of squares for model divided by sum of squares total. So 19.89 divided by 174 gives me an r-square of 0.11. It's pretty low r-square. So the within group variability is a lot bigger than the between group variability. So you're not explaining a lot. And then here's your stem and leaf plot of the scores. It gave me two of them with a different title. Distribution of scores. So this is 102, 302, 5, 7, and 902. What would you say looking at that?
It's like they all overlap.
It looks like there's a lot of overlap. I don't see a whole lot of difference between them. But remember, the p-value was significant. There's a 0.003 p-value. So sample sizes are big enough to overwhelm some of that variability, and there is at least one of the groups different than the rest. Well, which one would you guess is different than the rest?
Second one, right?
Second from the right is different than the rest?
I mean, it just looks like Or is that its sample size
Well,
that the whiskers are on? Or?
this diamond is the mean,
Okay.
and that test is testing
That's-
difference in means. So this first one looks to be lower than the others. This one's kind of in the middle, right? I'm out of time, so we'll quit there. We'll talk about the rest of this.
So what's the
Next
first
time.
one?
We'll talk about it. It's the first one was 102. So this tells me that 102 versus 302 is different. It's statistically different. So the first one and the second one, those two are different from each other. Yes.
Oh, it's all, I had another question I'll talk about.
Okay. All right. So we'll let you go, and we'll see you Wednesday.